Now let's investigate the algebraic properties of the cross product, and we have to be careful because the cross product, although it in a sense is a form of multiplication and acts a lot like multiplication, it doesn't satisfy a lot of the typical properties that multiplication satisfies. Well, first let's take a look at what happens when we cross the standard basis vectors with each other. So I would just like to note that when you cross any two standard basis vectors together, since each of them has magnitude 1, and since the angle between any two of them is pi over 2 and sine of pi over 2 is also 1, then the magnitude of the cross product of any of them is going to be 1. Any two distinct ones. Furthermore, since it's going to be perpendicular to the two given guys, if I take I and j and cross them, I'm going to have either k or negative k, because k and negative k are the unit vectors that are perpendicular to both I and j. How do we figure out which direction to go? Well, by definition, k points up if we go from I to j using the right hand rule. So I cross j is k. However, j cross I is going to be negative k, because when we take j first, we start at j and go to I. So we're actually curling our hand. If we're using the right hand rule, we're actually curling our fingers around this way. And so the cross product is going to point down. So we get negative k. Similarly, j cross k is I, because right hand rule says we're curling our fingers this way, the vector comes this way, whereas k cross j, we're curling our fingers the other way, it's going to be negative I. K cross I is going to be j, because we're curling our fingers this way, so j comes this way, and I cross k, we're curling our fingers the other way, so we get negative j. Also, I cross I is the zero vector, j cross j is the zero vector, k cross k is the zero vector. So that's everything. Now, the cross product by the above is not commutative. I cross j and j cross I are not the same thing. They are additive inverses. One is the negative of the other, so they're not the same. Okay, so you can't just swap the order of crossing two vectors. It's also not associative. The order in which you cross things matter. I can't just say I cross j and not tell you what to do first, because I cross I is 0. So if I cross I and I first and then I cross j, I get 0 cross j, which is 0. Whereas if I cross I and j first, I get k. Then I cross, the result of that is I cross k, which is negative j, and 0 and negative j are different. So the cross product doesn't satisfy these two basic properties that you might assume a lot of algebraic operations satisfy. That it's not commutative is not super crazy, because it's not too hard to come up with sort of operations that you can combine that don't commute with each other. However, that they're not associative is pretty weird, because usually a lot of mathematical operations, at least common ones, it doesn't really matter the order you do them in, but with the cross product, which is pretty basic, it does. That's pretty interesting to me. Anyways, so here are some properties. If a, b, and c are vectors and k is a scalar, then the cross product of a and b is equal to the negative of the cross products of b and a. This is called anti-commutativity. Anti-commutativity. They're anti-commutative. So instead of swapping the order, giving you the same thing, swapping the order gives you the negative. They behave well with respect to scalar multiplication. If I multiply a by k and then cross with b, it's the same thing as if I multiply b by k and then cross a against that. Or if I cross a and b first and then multiply against the scalar k. Okay. It's also left and right distributive. If you cross over addition on the left or on the right, it distributes over. Note that these are actually two distinct rules because we don't have commutativity. We do have to break it up into two distinct rules, I guess. Also, it has this interesting property with the dot product. If I cross B and C and then dot with A, it's the same thing if I cross A and B and then dot with C. In fact, we're going to study this quote-unquote triple product in a second. Finally, and this is something that I really can't remember ever using, but it's kind of cool. There is a way of sort of decomposing A cross B cross C. And if we do B cross C first, and it's A dot C, which is a scalar times the vector B, minus A dot B, which is a scalar times the vector C. Okay. In the interest of keeping myself honest, I'd like to make this about as fast as possible. This is not the most important thing, but this is interesting. The scalar triple product is A dot B cross C. And you can check that this is actually equal to the 3×3 determinant with rows given by the components of A, B, and C. Just think about it for a second. All right, so the fact is that if I take the magnitude of this, the absolute value of this determinant, it's equal to the volume of the parallelepiped determined by A, B, C. A parallelepiped is the three-dimensional generalization of a parallelogram. And this follows since the volume of this thing is equal to the area of the base times a height, and the height is the magnitude of A times the cosine of the angle between A and B cross C. And so the volume is the area times the height, which is the magnitude of B cross C. That's the parallelogram fact that we talked about before, times the height, which is the magnitude of A times the absolute value of cosine of theta. And well, the dot product is equal in absolute value to the magnitude of A times the magnitude of this other vector times the absolute value of the cosine of the angle between them. Fantastic. Did I say that this wasn't necessarily useful? Actually, yeah, it is kind of useful. The volume of a parallelepiped is going to be equal to 0 if either the height or the area of the base is equal to 0. If the height is equal to 0, then that means A lies in the plane given by B and C. If the base has area 0, then B and C lie on the same line. So A and BC form a plane, so they're coplanar. Great. And if they're coplanar, then the parallelepiped lies in the plane, so it's a two-dimensional object. It has 0 volume. So let's show that the vectors 2, 0, 1, 0, negative 1, 2, and negative 4, negative 1, 0 are coplanar. Do that by evaluating the volume of the parallelepiped spanned by them, and you do that by taking the scalar triple product. Great.